The story starts in 1959 at the Royal Radar Station in Malvern. This is actually the sports ground, the Pickersleigh Road sports ground of the Royal Radar Station, because otherwise I couldn't show you pictures. I took my camera on these days when we were working on this captured Würzburg set on the sports ground, because this was being used as a radio telescope to beam radar signals off distant objects, like, for example, the moon. And so 1959 was arguably the summer of the century. The Malvern Hills caught fire about every week, and so we had a nice time getting up to the gallery on this and putting up a 10-centimetre microwave maser, ruby maser, to amplify these expected small signal returns from distant objects. So that was my first introduction to the idea of masers. In fact, I'd asked to work on a project as a vacation student between my second and third years at the university on a maser, because I was very intrigued by the idea of masers and stimulated emission. And they allowed me to work with this team putting this ruby maser on this radio telescope. And I asked the people in charge of the group that year, could you ever make one of these things work at optical frequencies? Here we are with 10-centimetre wavelengths. Why can't we make one? And they could all think of about 10 different reasons why it wouldn't be possible. Clearly, the Charlow townspaper hadn't filtered as far as Malvern by the summer of '59. There may be some delay in publication or something, or getting the post to Malvern. It's a distant outpost after all. And they said, well, first of all, think of the way you make a maser. You make it with a 6-sided box of an order of a few wavelengths across. And these have to be highly reflecting size. Think how difficult that would be at optical frequencies. They also said, what on earth would you use as the pump? You don't have a klystron that can pump nice optical transitions like that. So that was all that I heard of it until the next summer, when I'd taken my degree at Nottingham and I was looking for somewhere to do a PhD. And my professor at Nottingham said, would you like to go to Oxford and interview there? So I did. I went to the Clarendon lab, and I came across a note from this person here, who's John Sanders, who was a fellow of Oriel College, but was on that year sabbatical leave to Bell Labs, working in Jim Gordon's group, in fact, at Bell Labs, Murray Hill. And in fact, you saw those pictures of the early maser pioneers with Professor Towns on the right-hand side and Basov and Prokhorov. Well, in fact, John Sanders is not in that picture. He took it. So anyway, he picked up these ideas about inversions of the population and getting a gas laser to work while he was in the Gordon group there. And you see, it says on leave from the Clarendon Laboratory, Oxford, England. And this is actually a picture of John probably about a couple of years later. It's probably about 1973 or something, I would say, that picture. Anyway, he wanted to recruit a student to work on optical masers. I read that note and said, that's what I want to do, because I knew from my previous summer at Malvern, if it worked, it would be really something great. In fact, the first lunch I had after that at the Eagle and Child, the Bird and Baby in Oxford, the other students who started that day all asked me, well, what on earth would you use this optical maser thing for, even if it works? I mean, what could you possibly use it for? And so I said, well, you might use it for some sort of communication. You might be able to shine a light beam and interrupt it, send more signals or something, or perhaps you could use it as a wavelength standard, because that was John Sanders' business. John Sanders was, in fact, a person who worked on fundamental standards, and his reason for getting into this field was because it looked like a promising way of getting very pure frequency or wavelength standards in the optical region. He published this paper proposing while he was still at Bell Labs, this letter to FISREV letters, and the very next entry in the journal is the Javan proposal for the helium neon laser. So it's exactly contemporary with the Javan proposal. So I started work in October 1960 to try and work towards an optical maser. Now, as you've heard, the Russian author, fabricant, had the correct ideas about what you would need in order to have gain, the ratio of populations and so on. So I built a piece of equipment which would look for gain, and John Sanders had gone to a meeting in the US at which a translation of one of Fabricant's papers was available. And it said that if you put mercury and hydrogen into a discharge and excited them, the hydrogen would quench the lower levels of the mercury atom and allow an inversion to exist. And Butayev and Fabricant actually claimed to have seen 10% gain down about a 50 centimetre path here in a discharge in a mercury-hydrogen mixture. So clearly, we dropped what we were doing and immediately moved over to mercury-hydrogen to put into our gain tube to see if we could see optical gain. Well, we did. We saw it on the green line, the violet line, and the blue lines of the mercury-bright triplet. And then I looked at the other lines, and lo and behold, there was gain there. And I looked at the ultraviolet lines, there was gain there. And the yellow lines, there was gain everywhere. And I thought, this cannot be right. So then I approached the makers of the photomultipliers tubes we were using and say, there must be something wrong with your photomultipliers because they seem to indicate positive gain when there isn't any. And John Sharp, in charge of the labs at the time, said, oh, well, that's a trivial effect. That's simply superlinearity. You know what happens if you change the working point of a photomultiplier, its gain actually increases. So the spontaneous emission from the discharge would actually flood the tube and cause the gain of the photomultiplier to increase, looking for all the world like true optical gain. So once we'd learned how to get rid of the effect, then all the Butayev Fabricant gain went away. In fact, we then published a paper saying we'd searched for light amplification. There was Mike Taylor as well in the group, and John Sanders and myself, and that was after about 2 years after I started that we got to that point. But at that point, all we knew that we had was an immeasurably small gain or loss, as it turned out. I certainly couldn't leave it there, so I spent the rest of the next 2 years, nailing down every parameter, measuring the populations at both the upper level and the lower level, and showing that even if you quenched out the lower level completely, you'd still need a tube about 5 kilometres long in order to see the kind of gain effect that Butayev and Fabricant were claiming. It was clearly, unfortunately, a spurious result. Here is a picture of the Clarendon Lab physics department at that time. At the front, you have the Brevis Blini and Willis Lamb, who was Professor of Theoretical Physics at the time at the lab. And then Nicholas Curti and Heine Kuhn are here in the front row. Somewhere buried in the Oipoloi at the back are myself and Ed Balick. Ed Balick was the technician that actually assembled the first helium neon laser in Bell Labs, the Javan Bennett Herriot laser. And although you didn't see him in the pictures, he was most certainly there and responsible for constructing it. He was an incredibly careful designer and engineer. He made the most beautiful equipment. And John Sanders offered him a contract to come and work for a PhD in Oxford and to have a contract with a salary at the same time. And this he took. And he came to Oxford and built this bake-out bench here. This is the oven that comes down. Now, this is actually the same room where Rudi Kompfner, just after the war, had done his work on travelling wave tubes. In fact, I inherited Rudi Kompfner's double-length slide rule, an absolutely beautiful Viennese-made slide rule that I used for many years. I never had any results more accurate than you needed a slide rule like that to work out, so that was fine. Ed built everything very carefully. These are all ultra-high vacuum. The whole laser was built on that bench there, and these are getter tubes of the rare gases. Everything in there was baked out at 400 degrees centigrade in ultra-high vacuum. So this is Ed's laser, which you can see in the exhibition, before it has his magnetic tuning coils put on it. And the mirrors are internal. This was before we knew about Brewster angle windows, before we knew about concave mirror cavities. These are plain mirrors, 1 metre apart. So they certainly needed, as Tony mentioned, an autocollimating telescope to get them near enough parallel. But Ed's big advance was to get this cavity made so nearly parallel that even without any external adjustment, he was almost in perfect optical alignment. And the final tweaking was done by just putting winding magnetic coils on these invar bars which contain nickel and therefore are magnetostrictive, and you can just pull it into final alignment by adjusting the current flowing in those bars. Now, I finished my degree in 64 and went across to Bell Labs to work with Gene Gordon's group on argon ion laser. The argon ion laser had just been discovered, and I was given the unique job of being able to run them into ground, destroy them, just to find out how they work, because nobody knew at that time how they really worked. In 007 in the lab, this is Ed's lab, the helium neon laser that is out there was here. You can see the RF excited discharge with its little external electrodes here, and all the cavities needed to measure it. This is an RF frequency spectrum analyzer, and Ed did some beautiful work on frequency pulling effects, and it was followed by Brian Garside, who did, again, some very elegant work on beating two different lasers together, showing that you could actually, with two independent sources, get beats stable enough to measure in the audio frequency region of the spectrum. And here's a single mode, two mode, three mode operation of these lasers. The precision with which Ed Barlick worked and the delicacy of these things, it was just a joy to behold. Then, again, while I was still in the States, Bill Sofast called me at Bell Labs and said, I've got a chance to go to Oxford and take up a postdoctoral fellowship there. Would you recommend it? I said, most certainly I would. So he came over and worked with John Deach, who's here in the audience, in -111, a basement room, the negative indicating it's in the basement. And they were able to measure huge gains in the 7229 superradiant transition of lead vapor, which is something that Bill Sofast had previously discovered when he was working as a graduate student in Utah. And here is the furnace, and the laser tube with the end of the laser tube sticking out here. And this was in some of the earliest work done on metal vapor lasers of any kind. And they were able to measure, here's a Fabry-Perot picture of the main ring and the subsidiary ring due to the other isotope, and measuring this gap here gives you the frequency difference between the isotope shift of that transition in lead. And not only that, they were able to get some new self-terminating laser transitions in calcium and strontium, and that was after Bill Sofast had gone back, and this was John Deach working with John Sanders in the Clarendon laboratory. So new laser transitions, self-terminating laser transitions in the ionized spectrum of calcium and strontium were discovered in those years. Also, a former student of John Sanders, John Ward, who'd been the last student, or the penultimate student, working on the frequency standard work, the fundamental standard work that John Sanders' group specialized in. He had gone over to Ann Arbor and worked with Peter Franken on the first nonlinear optics that was done anywhere in the world. And so, although John Ward was not himself engaged in laser work while he was at Oxford, when he went across to Ann Arbor, he quickly became involved in the laser work there. And he came back on a fellowship, the AEI fellowship that later I had myself, and he worked with a student, Jeff New, who's in the audience, on the first third harmonic generation in gases. So there's a variety of lasers used here with pulse lasers with high intensity and a gas cell and detection equipment to look at the third harmonic. And so what we have here is Jeff's plot of the power at third harmonic over the power at fundamental as a function of pressure. And you'll see that actually you get the most tripling efficiency for no gas at all. That is somewhat anomalous, and the reason is that the windows of the gas cell themselves have enough tripling capability to give you this point here. And when you put the gas in, you actually spoil the matching to some extent. But it is genuine third harmonic generation, because if you look at the way these things asymptote here, they indeed indicate that what the gas is doing is properly tripling. Now, Jeff is in the audience, and if you want to ask questions about this, I suggest you put them to him. The laboratory that supported a lot of the work that we did in these days was the Services Electronics Research Laboratory in Boulder, an old Navy laboratory, and Les Mathias and Crocker were responsible for finding many new laser transitions, again by nitrogen and water vapor and so on. Some of these are the longest wavelength transitions of their day in gas discharges. So there was a group at SERL, and just to put the sort of circulation list up here to give you some sort of idea, there's all these names from the past: Les Mathias, Harry Foster, all of these names. There's also a name amongst the circulation list, C. Hilson, but I often wonder what became of him. Well, you think micromachining is a new activity? Well, it goes well back 1966. With a pulsed gas laser, this group was able to show micromachining, actually only of thin films, but lifting films off a substrate by focusing a laser onto that. So a CW gas laser showing one of the first machining applications, although somewhat restricted in its application. And again, of that group, Doug Clooney's in the audience. Again, if you want to know more about that, there's again a person you can ask. Now, no talk on UK laser physics would be complete without a mention of Dan Bradley, who was a powerful moving force in the whole area. Dan lit a fire, if you like, under British laser physics. At Oxford, we were used to doing a man and a boy, sort of, and a dog maybe, but that was it. Very small groups, whereas Dan thought bigger altogether. This is his group in Belfast in '69, and you can see cast of hundreds. Actually, all male, all wearing jackets, and all quite tidy, but that's how it was in those days. And Dan was responsible for some of the, his group, for some of the short pulse laser development that has really led to today's short pulse lasers. In fact, Eugene Arthurs is again here, and this is the flash lamp pumped dye cell here, and a saturator absorber right up against the end mirror of the cavity, allowing you to pulse this into short pulses. 69, Bradley and Fergus O'Neill. And this was actually commercialized by a company that Dan founded, Electrophotonics, and these devices were sold to people, particularly in chemistry labs and so on, who wanted to use them for fast photolysis studies. So this was one of the first ventures into commercialism of a UK group. And the other thing that they developed was the detectors. And there's a name to conjure with. Wilson Sibbett was one of the members of that group at that time. It's amazing how many of the people from Bradley's group you come across in the... It was a big team, but they were all successful, and they all went on to do very valuable things in later life. And Wilson was particularly concerned with the streak camera developments and so on. And I'll leave him to speak for himself later on. There was also a great interest in getting tunable vacuum ultraviolet lasers, and although the original idea goes back a long way, the idea of using a molecule whose lower level was unstable against dissociation. You can have molecules which in the upper level are stable, bound states, and in the lower level just fall apart. That was around for some time, but the first people to realize it were the Russian group in liquefied rare gases, but one of the earliest gas phase XUV xenon lasers was the Bradley group, with Henry Hutchison, Malcolm McGeer, and that involved this device here, which is the electron beam accelerator, electron beam generator, which allows you to pump these gases in a vacuum diode. You have a vacuum vessel here surrounding a tube containing the high pressure rare gas, and the electrons, which are accelerated from the high voltage created by this, are accelerated into the medium and cause it to laze in the vacuum ultraviolet. Here's the high voltage supply, there's the tube containing the high pressure rare gas, and this again is a novelty, the first time ever tunable work by putting a lithium fluoride prism into here and tuning this laser gave you output in the vacuum ultraviolet which you could actually tune. Not only that, you could generate extreme ultraviolet radiation by using the third harmonic conversion from the xenon laser, and it goes up and up and it comes back down at 57 nanometers, 570 angstroms in the Lyman region of the spectrum. So, and you get a line which, by adjusting the prism, you can move around, so you can do some micro tuning of the output. Another name, which again one needs to recall from early days of lasers in the UK, is Arthur Maitland. He died in 1994, but he was responsible for starting a lot of the work at St Andrews University, and there's a very young Malcolm Dan working on one of the argon-ion lasers that Arthur Maitland built. They were building argon-ion lasers at the same time I was experimenting on them at Bell Labs, but Arthur had his own unique way of making these things. He made them out of discs of metal where they weren't enclosed within the vacuum, they were the vacuum enclosure medium. And he also had a unique form of cathode, which was quite a monster of a thing, but enabled you to get very high current densities down these lasers as you needed for that. And so a lot of the early argon-ion laser work was done in St Andrews by Arthur Maitland and Malcolm. Another group which certainly deserves mention because of its productivity of graduate students is Terry King at Schuster Laboratory in the University of Manchester. I mean, there's 65 PhD graduates. That's really quite something, including people like Chris Davis, who wrote a very good book on laser physics, Howard Baker, who now at Heriot-Watt works with Dennis Hall, and the others you can read, Costas, who's at Hellenic Research Institute in Athens. So they've done a lot of very good work. Like most people in the early days of laser work, they started on the helium neon and measuring the lifetimes of various levels in helium to see what possibilities there were for laser action and what problems they would have. But the thing that they really made a breakthrough in is the photolytic iodine laser, where you take a molecule containing iodine and flash photolyze it, and then the iodine that's produced is produced in the upper of two levels of the ground state. It's actually a split ground state in the iodine atom, and like as Professor Towns said, you can, by certain routes, produce molecules preferentially, or atoms in this case, in the upper of those two levels. And they reduced this to an engineered device, and in fact did gain-switched iodine at high pressures using a helium neon probe to measure the switching characteristics. These lasers were scaled in Germany and Garching to very big levels, almost at the sort of laser fusion sort of driver levels. In fact, they have been considered as a possible fusion driver at some point, although I don't think that's any longer current. At the other major government laboratory in the UK, the Royal Radar Station, Morgan, Roy Pike and colleagues were interested in photon statistics. In fact, I think when the they were able to measure correlations between photon emission times. And when the Glauber paper came out, I think it helped a lot in really understanding the differences between different light sources and their scattering mechanisms. And once again, I see Roy in the audience, so any questions on this can be directed to the originator. But this enabled people to do a lot of interesting applications. By looking at the geometric distribution of scattered photons and the correlations, one could get information about particle sizes and flow velocities. So this is a Maitland experiment on aero engines in the 70s, early 70s region, measuring the Doppler shifts that one gets from moving targets. And they were awarded the very prestigious Robert Award, and there's Eric Jacob on the left, and there's Roy, the other members of the group. And that, of course, has gone on to be very, very successfully commercialized through Brew Instruments, giving present status. The online particle sizing head is here, the nanoparticle sizing, and the device for ESA there. The interesting figure is that they have 40% of the world market in laser particle sizing, and you can read the number of noughts there in their annual sales. That is their present factory. So that's Brew Instruments. Another company that started out of a university laboratory was Brew Instruments, and that started from the spin-flip Raman lasers developed by Des Smith and colleagues, in which you take semiconductor indium antimonide and a very high magnetic field, and Raman shift the output of CW CO lasers or pulse CO2 lasers, and you can get tuning over the range between 5.2 and 6.5 microns, 9.2 and 13.8, and they are very, very narrow line output, so you can do with these some of the very first experiments in ultra-high resolution molecular spectroscopy were done using these very narrow bandwidth, 100 kilohertz sources. And the interesting thing is that what that led to in the way of products was actually products we have now that survive to today are the CO and CO2 lasers made by Brew Instruments for this commercialization of the spin-flip Raman laser. And those are still going on, still selling even today as one of the scientific CO laser productions. Of course, Southampton has always had a huge interest in optics, lasers, optoelectronics, and here is a picture of Dave Hanna, who's done so much pioneering work in the nonlinear optics field, and the papers they wrote on the first OPO in Proustite. And here's a early research student, 1973, Barry Luther Davis, who was using one of these Southampton-developed optical parametric oscillators to cover a wide tuning range in the infrared. Again, the person behind a lot of the work at Southampton, the fibre work, is Alex Gambling, who's in this picture here. But I'll leave Dave to speak about the work on fibres at Southampton. But a huge amount of work on lasers and laser devices has come out of Southampton. Again, a very big effort. To go back to my own group, around 1971, a young New Zealander, this is actually not Jim in 1971, this is Jim now, Jim Piper stuck his head around my door and said, "You got anything interesting a young New Zealander could do?" And I said, "Yeah, I'm sure I'll find you something interesting to do." And that was a very, very interesting 4 years when he stayed in my group from 71 to 75. We predicted and discovered more than 30 new CW laser transitions in metal rare gas transitions pumped by charge transfer, and in particular in ionized iodine and arsenic. We developed 35, I think, new transitions, and we developed a new form of laser for the copper laser, the neutral copper laser, the first transverse discharge excited copper laser. So we got interested in copper lasers in 1975, and it's just about the time Jim was going back, and he took one of those early lasers back with him to Australia. And in 1977, that became commercializable, and because they had very powerful outputs in the green and yellow, and also there's an analog in gold that puts out red, we got involved with isotope enrichment and also high-speed imaging for studying high-speed events. This was the culmination of what happened to the isotope enrichment. This is at British Nuclear Fuels Capenhurst plant, where a whole chain of these 100-watt amplifiers was set out, copper lasers, to pump dye lasers for isotope enrichment. And then the other thing that happened is that we were approached by the American Air Force, Dr. Fugate at Kirtland Air Force Base, to build a laser for a guide star. Now, I know it says in some of the literature out there that the first guide star for Keck was fitted in 2002. That may well be true, that the first guide star at Keck was fitted in 2002, but there was, in fact, a system built under Star Wars 1 a decade earlier at Kirtland, and the company that built it was Oxford Lasers, and here's a chain of copper lasers putting up a beam up into the sky that enables you to make effectively a spot in the sky. Actually, this is a spurious thing that's up there, just a high-altitude cloud. What you have is a pulse laser beam, and you just gate the time at which you get the return, and that gives you you've got 30 nanosecond pulses, you've got 30-foot lumps of light going up into the sky at the speed of light, and you wait until it's 10 kilometers downrange and gate on your detectors, and that gives you a spot that then you can use as a reference spot to apply adaptive optics to and correct for the distortion of the atmosphere. So this is an image taken way back in 1994. Unfortunately, this doesn't do it justice. You can see the original. You can see the shadow of this moon of Saturn, and another one in transit, a shadow of this one on the actual planetary disk. So we were involved in that work from very early times. My colleagues at Oxford Lasers wouldn't forgive me, however, for I actually believe we haven't done anything since then, and so this is what they're doing nowadays, ultra-high precision cutting and machining of small parts for the semiconductor industry. So I hope I've given you some idea of the sort of early laser work that went on in the UK, some of the developments that went on, and some of the people involved. I'm sorry I haven't been able to cover everybody's work. 35 minutes is not really time to do the subject full justice, but I hope I've given you some impression of what went on.